You might remember from yesterday, we revisited free body diagrams. We had introduced the concept a few days before, but we really didn't do much with it. We talked about it as a diagram in which that shows all of the forces acting on an object. Yesterday, we drew some free body diagrams and we explained why we need to draw these free body diagrams. Okay, let's do an example of a free body diagram first, and then we'll go back into why we need to draw these free body diagrams and how we're going to use these free body diagrams. So let me dictate a scenario here, and I want you to draw on your paper in front of you a free body diagram for this scenario, okay? We have a guy or a girl, doesn't matter, a person in an elevator. Okay, that elevator is accelerating upwards. In other words, you're on the ground floor, you're not just moving upwards at a constant speed, you're accelerating upwards, speeding up in the upwards direction. Please draw a free body diagram for the person in that elevator accelerating upwards. Okay, let's take a look at that. You can draw the elevator or not, it doesn't really matter. I'm just drawing the floor of the elevator and the person on the floor of the elevator. Tell me what one force is that's acting on that person that's standing on the floor of the elevator as he or she accelerates upward. What's one of them, Taylor? Good. The normal force, bless you, the normal force is going to act upwards. Remember what we said yesterday? It doesn't matter where we draw that, whether it's below the floor or above the floor, as long as we draw it in the right direction and as long as we draw it roughly to the right magnitude. Okay, there we go. That's the first one we drew, so it doesn't really matter how long we draw that one. The other ones that we draw have to be drawn relative to it. Right? The first one, pick a length. The other ones have to be drawn half as big, twice as big, same length, whatever, and in the right direction. What other forces do we have acting here on this person besides the normal force acting up on this person? Yep. Gravity is acting down. Good. Emma, is that what you're going to say? Okay, gravity is acting down. Emma, what do we know about gravity? Is it going to be bigger? Is it going to be smaller? Or is it going to be the same value as the normal force? Going to be equal to the normal force? Any more forces here? Yep. Okay, be careful with that. The force that's pulling the elevator up. Remember what the question was. Draw a free body diagram of the person in the elevator. What's pushing the person up? The floor. The floor is pushing the person up, right? What's pulling the elevator up? I don't care, because that would be a free body diagram for the elevator, not for the person. Make sense? These are the only two forces. Is this right now? Not quite. These are the only two forces, but it's not quite drawn right. What's wrong with it? If this elevator accelerates upward, then the forces must not balance, right? If the forces were equal and opposite, what would happen? It would go at a constant velocity. This would be when you're in that elevator and going to the 55th floor and you're at the 32nd floor. It's already reached a point of translational equilibrium. It's moving at a constant speed. It's accelerated all it needs to accelerate, and it's just going up at a constant speed now until the point where it has to slow down. So these forces aren't balanced. We should have drawn one of them longer than the other one. Which one should be longer? Gravity or the normal force? The normal force should be bigger. Yeah, the normal force should be bigger. If it accelerates upward, then that means the force upward has to be bigger than the force downward. That make sense? Let me give you another one. See what you can do with this. Let's go with, since you guys have a little bit of trouble with this one, let's go with another elevator one. Let's say this time you're moving downward in the elevator, going down really, really fast, and then you come to a stop. So you're slowing down as you're moving downward in the elevator. I want you to draw a free body diagram for the person in the elevator that is slowing down as he or she reaches the first story, the first floor of the building. Okay, let's have a look. Here's the person in the elevator. What force or forces act on this person in the elevator? Give me one of them. Sonia, what's one of the forces? Gravity, which way does it act? Okay, since we're drawing that one first, we can choose whatever length of the force that we want. Okay, let's draw it downwards like this. All right. What do we draw next? What other force or forces act on this? I don't know what other force or forces act on this guy in the elevator. Okay, so force, oh, sorry, I should have drawn that as, that should be gravity, right? That should be gravity acting downwards, right? That's what you had told me, right, Sonia? Yeah. Gravity acting downwards. And the other one you said is the normal force. Down, which way does it act? Yes. Tell me when to stop drawing it, okay? So in other words, when is it the right length, roughly? Okay? Right there. So the normal force is smaller than the force of gravity. Are there any more forces acting here? That's it. That's it. Is this drawn right now? There's something wrong with it. There's something wrong with it. What is it, Rally? Yeah. It should be the same as the other one, right? The normal force should be drawn greater than gravity. Why, Rally? Yeah, it's not. First of all, we know that they can't be the same length, so I'm glad you spotted that. Okay, they can't be the same length because it's not in translational equilibrium. Translational equilibrium means it's going at a constant speed and the forces are balanced. It's not at a constant speed, so the forces aren't balanced. One force is bigger than the other. Darwin, you caught that. Good. Okay, that's step one. Okay, now step two is to recognize, all right, if it's slowing down in the downward direction, which way does the net force have to be? If the force downward is bigger than the force upward, then what's going to happen to it as it goes downward? It's going to speed up, right? It's going to speed up downwards. So if we want it to slow down in the downward direction, then we need the upward force to be bigger than the downward force. That doesn't mean it's going to move upwards. If it was already moving downwards, it just means it's going to slow down. Right? It's like when you're driving your car and you put your foot on the brake. You're moving to the right. There's a force to the left. It doesn't mean you move to the left. It just means you slow down as you move to the right. Make sense? All right, one more free body diagram. We'll take it away from the elevators, though. Let's say this time we have a car. We have a car on the horizontal surface, this nice fancy box car. Let's say that this car is being pulled by a tow truck to the right with a force of 10,000 newtons. I'll call it FTT, the force of the tow truck of 10,000 newtons to the right. Let's say there's a force of air resistance that we'll call F air. It's a force of 2,000 newtons to the left. And there's a force of friction acting on this car of 3,000 newtons, and it's also to the left. Draw a free body diagram for that one, please. All right, let's tell me one force that acts on this car. One force, Noah, one force that acts on this car. Good. Which way does friction act on it? Okay, since we're drawing friction first, Noah, you can pick whichever one you want to draw first, right? Since we're drawing it first, we can make it whatever length we want to make it, right? We make the other ones relative to that. So friction is going to act to the left. I can draw that, by the way, wherever I want, as long as I have it drawn to the left, right? And what else do I got? Somebody else? Yep. Okay, I've got a force of the tow truck to the right. Tell me when to stop drawing the force of the tow truck, roughly. We don't have to measure it with a ruler, right? But roughly, when should I stop drawing the force of the tow truck? You know what? I'm going to draw it over here, actually. Can I draw the force of the tow truck over here? Tow trucks don't push cars. Is it okay to draw the force as if it's a pushing force? Yeah, sure. It doesn't matter where you draw it. The reason I'm going to draw it over there is because I got a bunch of numbers over here. It's just going to get in the way, right? So tell me roughly when to stop here. We'd like to probably go even a little bit further, but we can't really because we ran out of space there. That's okay. Okay, that's good enough. We can see that the force of the tow truck is clearly bigger than the force of friction. That's going to be 10,000 newtons. Make sure you have that arrow drawn so that you show it to the right. Olivia, give me one more force. Okay, the last one that I have at least written down here, the force of air resistance, it's 2,000 newtons to the left. We can draw that right here because we got some space. Tell me when to stop. Tell me when to stop drawing it, Olivia, okay? Roughly. Okay, yeah, that's a little bit shorter than the force of friction, so that works. I tell you on a quiz or a test, I'm never going to get a ruler out and measure to see if, oh, make sure that's exactly 2/3 the length of the force of friction. If it's a bit shorter than the force of friction, then I'll give you credit for that, right? Are there any more forces acting here? We don't have any more listed. We have gravity acting down. We don't know how big gravity is because we don't know the mass of this car, so we can't necessarily draw it proportional to the other ones, right? Any others? Yep. The normal force, in which way does it act? Yeah, and draw it wherever you want. I'll draw it right here. Same length as the force of gravity because it's on a flat horizontal surface and it's not accelerating up or downwards, right? Make sense? These two forces that I have drawn in red here, Fg and Fn, what do you notice about those two forces? I got them drawn in red for a reason here, to separate them, to differentiate them between the other two forces. And there's a reason that I've done that. How come? Rosie, how come? Yeah, I can cross them off. Okay, that simplifies things pretty dramatically, actually, by crossing these things off. I can cross them off because they're exactly the same values in opposite directions. If I happen to have a force of friction of 3,000 newtons to the left and an applied force of 3,000 newtons to the right, I could cross those off as well, right? But I don't have anything horizontally that will cancel out, that will cross off, because nothing that balances each other. Vertically, yes, and that happens a lot. Horizontally, nothing that balances. Do you guys remember what the next step would be in analyzing this problem? Now that I've drawn my free body diagram, let's say that you were asked to find the net force acting on this car. What would I do? What comes next? William, what comes next if I want to find the net force, the total force acting on this car? Yeah, we're going to say F net is equal to the sum of the forces. Don't just add them up, show the work, but in effect, that's, William, what you're going to do, is add them up. F net is equal to FTT plus FF plus F air. How come I chose that order to write them in? How come I chose that order? Yep. Yeah, I guess. Yeah, I guess. Honestly, there's not really a good reason why I did choose that order. That's the way that I have it drawn on the board. Doesn't matter what order you do it in, right? David, what's 1 plus 2 plus 3? Yeah, good. David, what's 3 plus 2 plus 1? What's 2 plus 1 plus 3? Look at how quickly he's nailing these now. Exactly the same, right? It doesn't matter what order we add them in. We get the same answer, right? Ft plus Ff plus F air, Ff plus F air plus Ft. It doesn't matter what order we do it in, right? Whatever way is convenient for you, whatever way you feel like doing it at the time. Let's plug some numbers in here now. FTT would be 10,000 newtons. FF would be 3,000 newtons. And F air would be 2,000 newtons. Is that right? Is that right? Ben, is that right? What's wrong? Good. So what do we got to do with that? Good. Usually we're going to say right is positive, left is negative. Doesn't really matter, but that's normally what we'll do. That's going to make the 10,000 newtons positive, the 3,000 newtons negative, and the 2,000 newtons negative. Good. Good. Now we're going to add these up. 10,000 plus negative 3,000 plus negative 2,000 gives me 5,000 newtons. The net force is 5,000 newtons to the right, which means that it's going to accelerate to the right, which makes sense, right? You got a tow truck pulling this thing. It accelerates in the direction the tow truck is pulling. Yep. Yes. Now, the next thing, we don't have to do this here because we don't know the mass of this car. But if we knew the mass of this car, I might ask you to find the acceleration. How would we do that? That next step, if I asked you to find the acceleration of this car that's being towed by the tow truck. Yeah. All we do is set F net also equal to M times A, and then we'd divide that net force, 5,000 newtons, by the mass. Because remember, first day we did Newton's second law a couple days ago, we said The net force is equal to M times A. Not force equals MA. The net force equals M times A. And the net force is 5,000 newtons. Does that make sense? All right, we had a couple questions for homework last night. Page 132. Either of those that you'd like to go over here? All right, if all those are good, let's take a look at another one here. 3.6 on page 150. This one says, two athletes on a team A and B are practicing to compete in a canoe race. Athlete A has a mass of 70. Athlete B has a mass of 75. The canoe has a mass of 20 kilograms. So this is getting a little bit cumbersome already, right? We got three different masses. Let's call this one person A with a mass of 70 kilograms. Let's call this one person B with a mass of 75 kilograms. And the canoe itself has a mass of 20 kilograms. Just trying to make sure I keep this straight. And oftentimes it's easier to keep it straight if we have a picture. A can exert an average force of 400 newtons forward, B 420 forward on the canoe using the paddles, but there's a magnitude of water resistance of 380 newtons. What's the initial acceleration of the canoe? I want somebody to come up here right now and draw on the board right now one of the forces. Okay, I don't want to do it. I want you to do it. That one's going to draw one of the forces acting on this canoe, whatever. Let's see what happens here. He's drawing a force to the left. Okay, he's going to label. He's saying it's 380 newtons, but he's going to label that as something. F. Since you're labeling this down, you get to pick whatever you want. You call that FC. What's that stand for? Okay, canoe's resistance. He's calling it FC. You might want to call it FW for the force of water, FWR, FR for the force of resistance. Call it whatever you want, right? You can say, you're the one there on the picture. You get to pick what it's called. Okay, FC, 380 newtons. Somebody else come up here and draw another force, please. Deanna's kindly volunteered to draw another force for us. She's drawing something to the right. Is it okay that she's drawing it where she's drawing it? We don't care where it's drawn, right? She's labeling 400 newtons. Hold on for a sec. We got to call that something. Let's call it FA since it's athlete A. Does that make sense? Is that good? Now she's drawn it just slightly longer than FC, I think. It's going to be pretty close to the same length, right? We're not going to lose any sleep over the difference between those two forces. Next up. Thank you, Miles, for volunteering to draw another one. Miles is going to draw something to the right. All right, he's drawing something bigger, it looks like. 420 newtons. And he's going to call that FB. Okay, that works. Okay, that works. Should be a little bit longer than the 400 newtons. So we've got 400, 420, and 380. Is there anything else acting on this canoe here? Oh, Anna, is there anything else acting on this canoe? Gravity is acting down. We don't actually know what its value is. We could find it, but we don't know what it is right now, right? And I'm not going to bother finding it. You're going to see why in just a second. Anything else? And how big should that be? Same as gravity. Okay, that's why I didn't bother finding the value of the force of gravity, because I know that gravity and the normal force are going to end up canceling out anyways. All right, this time we want to find the acceleration as opposed to the net force. So let's say, start off the same way. F net is equal to the sum of the forces, FC plus FA plus FB. But this time we're going to set F net equal to M times A as well. The net force is the sum of the forces, but the net force is also M times A, going back to the first day we introduced Newton's second law. Plug in some numbers. What mass do we use here? The 70 or the 75 or the 20? All of them added together. 70 plus 75 is 145, 165, I think, times the acceleration equals FC 380 plus FA is 400 plus FB is 420. Is that right? I'm going to ask Ben because I know Ben knows if this is right or not. No, what's wrong with it? Yep, good. Ben says they're going in different directions, so something's got to be negative. Probably the one that's to the left is going to be negative, and that's the 380 newtons here. So let's simplify this a little bit. We got 165 times A equals 20 plus 420 is 440. And A ends up being equal to 440 divided by 165. We get an answer of 2.7 meters per second squared. Okay, let's have a look at these questions on page 150, please. Okay, let's take a little bit of time to set this up in case anybody's having some trouble here. It says in the men's four-man bobsled event in the Winter Olympics, the maximum mass of a bobsled with two riders, a pilot, and a brakeman is 630 kilograms. So you got a sled, you got two riders, you got a pilot, and a brakeman. 4 people, okay, 630 kilograms. That's the maximum that you can have. Now the question goes on to say, during practice runs, riders A and B exert average forces of 1,220 newtons and 1,200 newtons respectively to accelerate the bobsled of mass 255 kilograms, the pilot and the brakeman. They jump in for the challenging ride down the 1,300-meter course. During the pushing, the magnitude of the force of friction is 430 newtons. What's the average acceleration of the bobsled, pilot, and brakeman? Here's the sled. We know there's a force of gravity acting on the sled that's acting downwards. We know there's a normal force acting upwards. I don't know what those values are. We could find them, but we're not going to bother because we know they're going to cancel out anyways, as they usually do. What else we got here? It says during the pushing, the magnitude of the force of friction acting on the bobsled is 430 newtons. So we're going to draw FF, the force of friction, to the left. Assuming it's moving to the right, we're going to say FF is 430 newtons. What else do I got? I got 2 other forces, right? Rider A pushing with 1220 newtons to the right. We'll call that FA. And rider B is 1200 newtons to the right, just slightly shorter than FA. I think that's it, isn't it? What mass do I use here? What mass do I use? 630, 255, 98, 97, or some kind of combination of those masses. What mass do I end up using here? Yep. Yeah, I use the 255 and the 98 and the 97. The reason I use those 3 masses and not the 630 is this. The question says, during the pushing, the force of friction is 430. What's the average acceleration of the bobsled, pilot, and brakeman? There's 2 guys pushing. Why do we not include their mass? Because they're not in the bobsled yet. They're doing the pushing. Like in that example that I gave you before, the tow truck was doing the pulling. Did we pay any attention in that question that we did before about the mass of the tow truck? We don't care what does the pushing or pulling. We don't care how heavy it is. We care about the mass of what's being pushed or pulled. You got 2 guys and the sled that's being pushed. You don't have the other 2 guys being pushed. You have the other 2 guys doing the pushing. They're like the tow trucks. We draw those forces, but we don't care how much they weigh. We're going to say the mass here, 255, 98, and 97. I think that gives me, technically a free body diagram shows forces, not masses, but we got to write down givens. So we might as well write down the mass along with it, even though technically it's not part of the free body diagram. All right, give you a few more minutes to finish up based on what we have up here now on the board. All right, let's finish this off now. Okay, we got a free body diagram drawn. This is almost an easy question now, right? If we remember the steps, it's almost an easy question. The tough thing was the free body diagram and recognizing that the mass was 450. We're going to say the net force is equal to the sum of the forces, FF plus FA plus FB, or whatever you call them. Seems like logical names, but whatever you call them. What is F net also equal to? Yeah, yeah, mass times acceleration. So we'll say ma is equal to FF plus FA plus FB. And then we'll start subbing in numbers here. The mass is 450. Looking for the acceleration. FF is negative 430. Okay. We all know, especially Ben knows, that the force is going to be negative because it's acting to the left. FA is positive 1220. And FB is positive 1200. We add those forces up on the right-hand side. We end up getting 1990 newtons. We divide that by 450. And we end up getting 4.4 meters per second squared for the acceleration. Two significant figures, right? Or wait a second. Is it two sig figs? 1220 is 4, 4, 3, 2, 2, 3. Two sig figs is our final answer, right? Hey, I got one for you. What if this number had been one significant digit? It's not, it's 3, right? What if it had been one significant digit? Would that have changed our answer? Our final answer would still be 2 digits, right? Because we didn't use that number. So that's 3, so it doesn't really matter, but it's an irrelevant number anyways. We don't count sig figs on numbers that we didn't use. Okay. All right, I got a few questions for you to work on for homework. There's only 4 of them. Page 136, I have listed there 1 to 4 and 8, but as I was planning this, I wanted 1, 3, 4, and 8. 1, 3, 4, and 8. Give you a chance for a couple of minutes to work on those questions now.